Let's get that going. Let's begin. So today we are starting now on chapter 3 of the book. I think it's the biggest chapter. Chapter 3 is now introducing derivatives. What a derivative is, our rules for derivatives, and then chapter 4 will be doing applications of derivatives. So chapter 3 and chapter 4 together is 1/3 of our whole school year, basically, or 1/3 of the material that we cover. So huge part of the class, huge part of the material. Now the nice part is I already introduced you to exactly what a derivative was clear back when we started calculus proper. Clear back when we were first talking about limits and what a limit is. So let's remind you a bit of how that discussion went. So first off, intuitively speaking, what is a derivative? It gives you the slope. That's intuitively what it gives you, the slope. What's the derivative of a function at a point? It's the slope of the function at that point. Okay. Question, what is the derivative of this function? How much does it slope? It doesn't, so its derivative is 0. And if we looked at a vertical line, what would its derivative be at that point? Undefined. Okay? So intuitively, a derivative is just a slope. And so if I gave you, that's a nasty piece of chalk. If I gave you some random function like this, and I asked you, what's the derivative at this point? And it's asking, what's the slope at that point? And it looks like it's about -1. Just looking at the picture is roughly what it should be. What would the slope of the function be at this point? Should be 0. So the derivative at that point will be 0. And the derivative at this point, maybe that's more like a -3. I don't know. But just roughly looking at the picture, quick sanity checks for what derivative should be at points. So intuitively, the derivative of a function at a point gives you the slope of the function at the point. That's all it does. Okay. So let's restart a conversation talking about lines and where these slope things come from. So first off, in order to define a line, what do I need? Going back to your geometry, what do you need to define a line? You need 2 points. 2 points gives you a line. If I said, I have a particular line in mind and I want you to come draw it, what do I need to give you in order for you to draw that line? 2 points. I need to give you 2 points, or something logically equivalent to 2 points. So pick any random 2 points, x1, y1, x2, y2. Here's 2 random points that we picked. Okay. And now we want to talk about this line, the set of all points on this line, x, y. What are all the points on this line going to have in common? They all give us the same slope.
Same slope.
They all maintain the slope.
Yes.
Right? So pick now, so we got x1, y1, x2, y2, and we drew a line through them. Now pick any other random point on the line, x, y. Here's some other random point on the line. Right?
Yep.
What is the slope from here to here? How do I get the slope between those 2 points? You just do rise over run.
Delta x.
It's just rise over run, right?
Yeah, y2 minus.
How much does it go up? It goes up, y2 minus y1. How far over do we go?
x1.
x2 minus x1. Right?
Yeah.
Similarly, looking at these 2 points, what's my rise? It's just y minus y1. And what's my run? It's just x minus x1. You with me?
Yep.
Yeah.
And so, y minus y1 over x minus x1 has to equal y2 minus y1 over x2 minus x1. For any point x, y you pick on this line.
Okay.
Make sense?
Mm-hmm.
And this is where your equation from the line comes from. I take this, multiply both sides by x minus x1. So that cancels out top and bottom over here, and you get an x minus x1 over there. That's all we did to get here.
Okay.
Right?
Yeah.
And you've seen that equation of the line several times. It's called your 2-point form, or whatever it's called. Where you take 2 points, plug them in for y1, y2, x1, x2, and that will give you the equation of a line going through 2 points. We have a special symbol for the slope of a line. We call that m. And so just substituting the slope with m, this is just the slope, m.
Yep.
Just substituting that out, you get y minus y1 equals m times x minus x1, or the point slope form of a line.
Okay.
Do a little bit of algebra. M times x is mx. M times negative x1 is negative mx1. And then plus y1 to both sides moves it over there. You see that?
Yep.
Now, this whole garbage term right here is just a bunch of constants multiplied and added together. What are all these equal to? Notice that they're equal to y when we plug in 0 for x. If you plug in 0 for x, what's y? This term goes away. Y is negative m times x1 plus y1.
Yeah.
Right? So we call that junk. That's whatever y is when x is 0, and we replace it with just a symbol b. It gives you the y corresponding to x being 0, or the y-intercept.
Oh, okay.
Right? So standard stuff for a line. Now, a couple different ways that we could talk about the slope of some line. And if we let delta y be our rise and delta x be our run, then it's just delta y over delta x. Right?
Yes.
Another way we could have written that is, what is delta y? It's y minus y1 over x minus x1.
Minus x1. Yep.
No difference. Y, sometimes we say y, if y is equal to f of x, some function in terms of x, then y is just f of x.
Yeah.
And what is y1? It's just the value that you get at f of x1. So f of x1 is the same thing as y1, right? And f of x is the same thing as y, and f of x2 is the same thing as y2.
Okay.
They're all the same thing, right?
Yeah.
So just replacing your y's with f of x and f of x minus 1, same thing. Going from here to here. See it?
Yeah.
Okay. Now, notice, that should be an x1. Notice that x is just, take your starting point and add how far you went.
Okay.
So it's just x1 plus delta x, get you x.
Yeah.
So x is the same thing as x1 plus delta x,
Okay.
right?
Yep.
And x minus x1 is obviously the same thing as delta x. X minus our ending point minus our starting point gives us our distance.
Yeah.
So replace x minus x1 with delta x, and so we get f of x1 plus delta x minus f of x1.
Wait.
These are all different ways of just writing the slope.
Wouldn't it be displacement, not distance?
In this case, they're both the same.
Okay.
Because we're only ever going to talk about 2 points at a time. We're not going to talk about going there, then back, then there, then back, da 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 da.
Yeah.
Okay. We're missing Caleb. So, these are all logical equivalent ways of writing the slope. All I'm worried about for you guys with these first two sections, in terms of the concepts, it's not going to be anything new. It's just that there's going to be tons of notation for the exact same thing. And you got to get comfortable with the different notation. And some notation is going to be convenient for one problem, and other notation for another problem.
Yeah.
And so you just got to get used to using the notation that's convenient.
Right.
So these are all different ways of writing the slope. Now we get to a derivative. What is a derivative of a function at a point? It's the slope of the function at a point. How do we find the slope of a function at a point? So imagine I've got this function here, this curved function, and I want to find the slope of this function at this point x9.
Okay.
We need 2 points to get a slope. I can't just talk about the slope at 1 point. I need 2 points to get a slope. So I pick some other point x, find where it is on the function, and now I draw the line that goes through both those points.
Okay.
And I say that the line that goes through both those points, its slope is an approximation for the slope at this point, right?
Mm-hmm.
Now, this isn't a great approximation. It would have been better if I chose a closer x. If I would have chosen my x to instead be right there, then our second point would have been right there. Our f of x comes out right here. And now, this line that goes through these 2 points is going to be a better approximation of the slope at that point, right?
At that point.
Yeah, and if I let my x get even closer, then I get an even better approximation.
Yeah.
And as I let my x get arbitrarily close, my approximation gets arbitrarily good.
Yeah.
And so, what is the derivative of this function at that point? What is the slope of this function at that point? It's the limit as x approaches x naught of the slope.
Okay.
Right?
Yeah. Yeah.
That's all a derivative is. It's the limit of a slope as the 2 points get arbitrarily close together.
Okay, yeah, that makes sense.
So the limit as x approaches x naught of our rise over our run.
Yeah.
That is the slope at x naught. And we have this notation now to talk about that. We call that f prime at x naught. One of the ways that we write a derivative.
Okay.
So what is f prime of x naught? It is the slope of the function f at the point x naught. And it's equal to this limit right here. You with me?
Yep.
Now, it doesn't really matter what notation I used right here. The concept is, it's just the limit of the slope. Right?
Yeah.
And so we have different ways we can write the slope. I could have used this notation. That's the notation I'm using right here. I could have used this notation. What else is the slope? It's the height at f of x naught plus delta x minus the height at f of x naught. So how much it went up over your distance delta x divided by delta x.
Yeah.
And now, this time, we're not taking the limit as x approaches x naught. We just take the limit as delta x goes to 0. But they're logically equivalent. They mean the same thing. As x approaches x naught, the distance between them, delta x approaches 0.
Yeah.
Exact same thing. This is going to be the hard part early on, is thinking about the exact same thing with different notations. Now, for some reason, H caught on rather than using delta x in math textbooks.
Yeah.
And it's a newer thing. So your older math textbooks are more likely to use a delta x. Our textbook that we're using is a newer one. And so they said use H. H and delta x mean the exact same thing.
Okay, that helps.
So I don't know why they do this. I don't know where it comes from. But if you think let H equal delta x, then that gets you this. Identical. Means the same thing.
Yeah.
I like the delta x notation better. I think it's more clear what you're talking about.
Mm-hmm.
But this is the one that is used most frequently in the book. So tough luck. And then finally, it's the same thing as this. It's the limit as x approaches c. If you want to find, if we would have called this a point c, it doesn't matter that we called it x naught. If I said this is the point c, now what's the derivative of this function at the point c? Then it's now this. It's the limit as x approaches c of f of x minus f of c over x minus c.
What's the point of adding that c one?
The point is, I used an x naught there. There's nothing magical about that symbol.
Yeah.
I could have used a c. So we've been talking about the limit. We've already been talking about, is a function continuous at a point c? You might say, does a function have a derivative at a point c? And so here's the natural notation to use.
Okay.
So a bunch of different notations all saying the same thing. It's just the limit of the slope. Or, this is also often referred to as the difference quotient. What's a quotient? It's division.
Of the division.
So, and what's a difference? It's when you subtract two things.
Yeah.
So this is often referred to as the difference quotient. So what's a derivative? It's a limit of a difference quotient. A limit of a slope. Two ways it's often said using high-level language. Good so far?
Yep.
All right, let's get into some concrete examples. Let's look at just some line, f of x equals mx plus b.
Okay.
You with me?
Yeah.
Let's find the derivative of this function at some point. Give me a point.
3.
3. Let's find the derivative at x equals 3. So if you go over to 3, what should the slope of the function be? M, whatever the slope is. M,
Oh.
right?
Yeah.
What about if we would have found the derivative at -1? What's the slope at -1? What about at 19? And so no matter what, our derivative should come out m. So if this is graphing f of x, here's f of x graphed, then here's f prime of x graphed. All our derivatives. What's the slope of this function at this point? M. What's the slope here? M. What's the slope here? M.
Yeah.
You with me? Now let's actually calculate it using our definitions here and see that that's how it comes out.
Okay.
Okay. Which one should we use? Which notation?
The delta x.
The delta x one. Okay, so we'll use this notation. And I'll just use different notations for each of the example problems, get you comfortable with all the different ones.
Okay.
So we'll use this one. So I am looking for the limit as delta x approaches 0 of f of, what's the point that we care about?
Delta. Oh, F naught, or X naught.
Yeah, in our special case, what is it? We're finding the slope at which point?
3.
3.
Oh,
So we're looking at 3 plus delta x. Sorry. 3 plus delta x minus f of 3 all over
delta X.
delta x. That's the limit we're trying to calculate. So our question is, what does this equal? That's what we're trying to figure out.
Okay.
Good so far?
Yeah, we're good.
Okay. So now that we picked one of our definitions, now you just solve it the way you've been solving limits this whole time. Nothing special about it. It's just always going to be the case. Notice that every single time your denominator goes to 0.
Yeah, that's.
And so the whole trick, always and forever, is somehow canceling out with your denominator, just like you've been doing with limits.
Yeah.
So, writing this out, we're calculating the limit of, we'll start right there and then just write what this is equal to. So this is equal to, plug in 3 plus delta x into that function. So I'm plugging that into my function there.
Oh.
So replace all our x's with 3 plus delta x. So it's going to be m times 3 plus delta x plus b.
Yeah.
And now we need to minus what we get when we plug 3 into the function.
Okay.
What do I get when I plug 3 into this function? When I replace x with 3? I get 3m.
Plus B.
And then minus b since I'm subtracting that whole thing. You with me?
Okay.
All over delta x still, right?
Okay.
And now this is equal to, we have 3m plus m times delta x.
Delta X.
Notice that the b and the b cancel out.
Yep.
And then we have minus 3m. Didn't want to cancel out too soon in case you didn't see it.
Okay, gotcha.
You see that the 3m's go out?
Yep.
And you see that, maybe just be careful, which is equal to m times delta x
Over delta X.
over delta x. And now what can we finally do?
Cancel.
Cancel out the delta x top and bottom. Now this is equal to n. Now we need to find the limit of this as delta x goes to 0. So end our bracket here. So we were saying the limit as delta x goes to 0 of this whole thing. And what's it equal to?
0.
What's the limit of a constant as delta x goes to 0?
The constant.
It's just a constant. What's the limit of 7 as x approaches 0? 7. It doesn't care. So the limit of m is just m. And shocker, the slope at 3 came out m. Now notice that 3 didn't even end up mattering here. It's completely gone from our answer.
Yep.
So in general, if I would have said at some point x naught, any x naught now,
Any number.
then we would have had a 3, we would have had x naught here, 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 and they all cancel out. And so pick any point x naught you want. What's the derivative? M. So slope everywhere on that function is m. And so if we wanted to now talk about the derivative of this as a function, what is the derivative of this? It's just m. If this is your f of x, this is your derivative of f of x.
Okay.
This gives you the slope at any point x. And so we have that graph right here. All right, repeat. Let's do this again. This time, the author wanted us to take the function f of x equals x squared and find the tangent line to the function at the point 2, 4.
Okay.
So we're looking for the tangent line. With me? Now, the tangent line, we need the slope. Once we have the slope, then, looking at our equation of a line, we'll use this equation to get the equation of the line.
Yep.
This is the equation of a line with a slope m, and that goes through the point x1, y1, or in our case, 2, 4.
So we need to find the slope first.
So we need to find the slope first. Which one should we use?
We should use the C.
The c one?
Yep.
All right, we'll use this one. So we want to look for the limit as x approaches. What are we approaching in our case?
C. X of 2.
2. C is an actual number. So in this case, we're looking for the limit as x approaches 2 of our function of f of, just plug in here, f of x.
2.
No,
Wait,
this one's
that
x.
would, yeah, that'd be x.
Minus f of 2 all over x minus 2.
How did you get, oh, okay, I got you.
Good?
Yep.
Okay, now, it's just calculating the limit the way you know and love. Our problem is our denominator is going to 0. We got to fix that. So we'll take our limit after we keep messing with this to see what it equals.
Yep.
Okay, so this is equal to, what is f of x? X squared.
4.
Minus f of 2 is 4. All over x minus 2, right?
Yep.
Now that's a difference of squares, so it factors into x minus 2 and x plus 2. All over x minus 2. Right? And now what do you see?
They cancel out.
X minus 2 cancels top and bottom, leaving us with
4.
x plus 2, right? And now take our limit. Take the limit as x approaches 2 of x plus 2, and what do we get?
4.
4. So the slope at 2 is 4. You with me?
Didn't they tell you that in the y?
No, that was the height. The slope and the height happen to be the same thing.
Okay.
That's not always the case.
Yeah.
Okay, so now what is our tangent line? Our tangent line is y minus, what's y1?
What's y1?
Uh-huh. So now I'm plugging into this equation to find the equation of this tangent line.
Oh, it's 4.
4. So y minus 4 is equal to m. What's our m?
4.
4. That's what we were just solving. 4 times x minus
2.
2. And then you solve it out. Whatever it comes to is whatever it comes to. Right?
Yep.
Well, we can just do it real quick. It's going to be equal to 4x. We'll get 4 times negative 2 is negative 8, plus 4 is going to be negative 4. So if we were to graph this thing correctly, it would have had crossed down here at minus 4, and this line should have a slope of 4.
Okay.
Right?
Yep.
So that was finding the tangent at that point. But let's also just find the derivative at any point x naught. So now let's find the derivative of this function at any point x naught. You with me? Rather than at our special number 2.
Okay.
So let's see how it behaves at any point. So we know at 2 it goes to 4. Let's see what it does at any point. Well, what do? Rather than 2's, we just have x naught, right?
Yep.
So x naught minus x naught squared over x naught. That would have factored x naught,
Well, the
x naught, and we would be taking the limit as x approaches x naught, right?
yeah, but
And
how
now
does
what
this-
does this equal? What is the limit as x approaches x naught of x plus x naught?
2x naught.
Just 2x naught.
Okay.
So what is the slope at 2?
4.
What is the slope at 3?
6.
What's the slope at 0?
0.
And notice that 0, the slope is 0. What's the slope at negative 1?
Negative 2.
Negative 2. So over here, if you go to negative 1, it should have a slope there at negative 2. And so in general, our f prime of x function, our derivative function, is just equal to 2x. This function is a derivative of that function.
Yeah.
This function gives you the slope at any point of this function.
Okay.
And you'll learn how to calculate these derivatives in your head. This is very trivial. A lot of work for something that people who've already taken calculus could just look at that and say, oh, 2x. And you'll get to the point you can do that. It's very easy. But we're going to start out by making you calculate by hand so you understand the concept of what's going on. And understand that when you're calculating a derivative, you're taking a limit of a slope. You're taking a limit of a difference quotient. So calculating by hand can be tedious. And so here's a graph of the derivative of this function.
Okay.
So if this is f of x, then here's your f prime of x. Make sense?
Only at a certain point, though.
Yeah, but now we can do it for any point. This now works for any point.
Okay.
So you can do it for a certain point, which is when we plugged in 2, and then you can do it for any point x naught. And we did it in both cases. Make sense? Okay, let's try another one. The author wants us to, I can't remember exactly what he says for this problem. He says, find the slope at the point A. So we want to find the slope at x equal to A of 1 over x. 1 over x roughly looks like this.
Yep.
Now, where can't we find the slope? Zero.
Oh.
So he says where x is equal to a and a is not equal to 0 because this function doesn't have a slope at 0. It's not even defined at 0.
Okay, I got you.
It can't have a slope where it's not defined. Your derivative function's domain is always as big or smaller than your initial function's domain. So if the function wasn't defined at a point, it definitely can't have a slope at that point.
Yeah.
Okay, so let's calculate now the slope of this function at the point A, or the derivative of this function at the point A. Which one should we use?
Top one.
The top one. This one?
Yep.
So this time we're going to do the limit. That's the one we did last time. Let's use the H one. I don't think we've done
We
this one
did
yet.
the C one, but we did the H one.
Oh, these are identical. I was just telling you x naught isn't special.
Yeah.
Okay. Of course, I guess they're all in a sense identical.
Yeah, that's.
Okay, let's use the authors. We'll do the limit as h approaches 0 of 1 over x. Okay? Or sorry, not of 1 over x. Of f of x plus h minus f of x all over h. Right? And now, obviously, we can't take the limit right away because we have h in the denominator and h is going to 0. Get rid of that bracket because we'll take our limit after we manipulate the thing. Okay, just plugging in, what is this equal to? What is f of x plus h? It's 1 over x plus h. Just taking x plus h, plugging it into that function. Right?
Oh. Okay.
Minus what? Just 1 over x. All over h. You with me?
Okay.
Now I'm going to get a common denominator in the numerator. In other words, I'm going to multiply this one top and bottom by x, and this one top and bottom by x plus h.
Why? How did you get that x plus h in the denominator? The
I'm
plus h.
plugging it into this function.
I know, but wouldn't plus h be on the side of it?
No. You replace your x with x plus h.
Oh. Okay, yeah.
Okay. So now, this is equal to, multiply this top and bottom by x. I'm going to get x over x times x plus h. That's rewriting this term. Multiplying it top and bottom by x.
Okay.
Minus, take this term, multiply it top and bottom by x plus h. So that's going to be minus x plus h all over x times x plus h. You with me?
Okay.
And then dividing by h is the same thing as just multiplying by 1 over h. Dividing by 3 is the same thing as multiplying by 1/3.
Yeah.
Okay, so now this is equal to, we now have a common denominator, so in our top here I have x minus h.
Plus h. Oh, yeah.
Distribute your minus. So we get negative h all over x times x plus h all times 1 over h. Right?
Wouldn't that cancel the 0? The denominator?
Well, now we can cancel. So now h and negative h cancel out, leaving what up here?
1 or negative 1.
Negative 1. So now it's negative 1 over x times x plus h. You with me?
Yep.
Okay, now we don't have something in the denominator going to 0, so we can take our limit. And so what's the limit of this thing now as h approaches 0?
Negative 1 over x squared.
Just negative 1 over x squared. Oh, oops. This is the slope at x. We were supposed to do it at a. Just a different letter. I was just using x's instead of h. Doesn't matter. So our derivative function, f prime of x, is equal to negative 1 over x squared. And so obviously, what is the slope at a is the same thing as saying what is f prime at a equal to?
It's equal to negative 1 over x squared.
It's negative 1 over a squared.
Or a squared.
What is the slope of this function at, give me a point,
6.
6 equal to? Negative 1 over 36. That is a very shallow negative slope. Look at this function. If I go clear over to 36, then that function is almost completely horizontal.
Yeah.
But it's still just decreasing a little bit. So it has a really small negative slope. That's what we would expect. What would we expect the slope at 1 to be? About negative 1, right?
Yeah.
Well, let's check that. What is f prime of 1 equal to?
Negative 1.
Negative 1 over 1 squared, which is just negative 1. Our intuition was right. Oh, that was at 1. At 1 it's negative 1, but at negative 1 it's also negative 1. No, the slope is always negative. Look at this function. It's always decreasing as you go that way.
Yeah, I see it.
Getting lower, getting lower, getting lower, reset, getting lower, getting lower, getting lower. And so the derivative of this function is f of x equals negative 1 over x squared, which is this right here.
Yeah.
This is mapping the slope of this at any point.
Okay.
Right? What's the slope right here? Negative a small number. What is the height of the function right here? Negative a small number. What is the slope of the function right here? Negative a really big number.
Yeah.
What is the height of the function right here? Negative a really big number. The height of all these points is mapping the slope of these points. The height of all these points is mapping the slope of all these points. The height of all these points is mapping the slope of all these points.
Okay.
Make sense? Okay. Let's now go back to one of the earliest problems that we did when we introduced this rate of change stuff. We talked about dropping a rock off a cliff or something like that. Now, it was given to you that how much that rock moves in a given time is given to you by this equation. F of t is equal to 16t squared. So in other words, after 1 second, the rock has gone 16 feet. After 2 seconds, the rock has gone 64 feet.
Okay.
After, we'll go straight to 4. After 4 seconds, the rock has gone,
Whatever 16 times 16 is.
which is,
I don't know.
all right, 256. But so this thing is obviously speeding up as it's going, right?
Yeah.
In going from 0 to 2 seconds, it only moved a total of how far?
256.
64. So in 2 seconds, it's gone 64 feet.
Yeah.
By the time we go to 4 seconds, it's already gone 256 feet, which is way more than just double that, right?
Yep.
It's double the double of that. So it's speeding up as it goes. Okay, so our problem now is to find the speed of the rock at some particular time. Let's start with a concrete number, then we'll do with a variable number. So what time should we pick?
6 seconds.
6 seconds? That's kind of way down there. All right, we'll find out how fast this is going after 6 seconds.
Okay.
Okay, so how do we find the speed of the object at a particular time?
We have it.
It's going to be our rate of change. We need displacement over time gives you the speed.
Yeah, but we have that speed already.
No. What's the speed?
Oh,
We just know where it is.
Okay, yeah.
We do not have its speed,
We have the time, I mean.
right?
Yeah.
So we want to calculate its speed after 6 seconds. Then what we're looking for is how fast it's moving. How would you measure that? We basically need to see, after 6 seconds, see how much it moves in like a small interval of time, and then divide it by that small interval of time
Instantaneous speed.
to get the instantaneous speed. It's the same concept here, in other words. In other words, the speed of this function is going to be the slope of the function. The speed of the object is going to be the slope of this function. Those are one and the same thing. Because how do you get the speed? How do I measure the speed of something? Imagine we physically did this. I want to measure your speed. I had you running really, really fast, and I would have like a meter stick right here, right?
Yeah.
And as you're running past, I start the timer right as you get right here, and I end the timer right as you get right there. And I say your total distance divided by your total time gives me your speed.
Okay.
Well, for our object, what is its total distance over some time interval going to be? It's going to be just f of t plus our time interval minus wherever it was at the start of our time interval. Maybe call that a t naught if you want. All over whatever our small time interval is that we used, 1 second or whatever.
Okay.
Your ending position minus your starting position divided by the amount of time I was measuring it over. Right? If you're running and I measure your speed for 2 seconds, and in 2 seconds you went 19 feet, if you went 19 feet in 2 seconds, what's your speed?
Whatever that is.
9.5 feet per second. This divided by this.
Yeah.
So here's your displacement over this amount of time. You with me?
Okay.
But we need to find it at exactly 6. It's the same concept as finding a derivative at 6. You see how this is the exact same thing as this formula right here?
Mm-hmm.
And so what are we looking for? We are looking for now solving our problem. Our problem, we are looking for the limit as delta t approaches 0 of f of 6 plus delta t minus f of 6 all over delta t. How fast is the object going at 6 seconds? What do? We look at it a teeny bit after 6 seconds.
Which is the approaches? What determines a little bit?
Delta t is, remember, it starts out with, who cares, some distance here, but then we take smaller and smaller ones.
Yeah, so approaches.
So we're making delta t get smaller and smaller. So the time interval that I time you over is going to get smaller and smaller and smaller and smaller.
Yeah.
And so it's going to be more and more accurate for that exact time. Because maybe as I'm timing you running, you slow down and speed up at parts of the interval that I'm timing you for.
Yeah.
Or this rock falling, obviously we know that this rock is speeding up as it falls.
Yeah.
So we don't want to use too big of a time interval because the speed's changing. The smaller the time interval, the less the speed changes over that time interval. So we're going to take the limit as our time interval goes to 0 of the sink.
Okay.
This is internalizing the problem. Once you get here, it's just the same as everything else. Okay, just calculate this limit the same way we've been doing all these problems. And how do we do it? Just flat plug it in. So 6 plus delta t squared, so this is equal to, we'll calculate the limit when we're ready to go. So I'm just going to leave it as 16 times 6 squared times, this is 6 plus delta t, sorry. 6 plus delta t squared minus 16 times 6 squared all over delta t.
Yep.
With me so far? Just flat out plugging that into there. The reason I'm not going to multiply out these numbers is because we're going to come back and replace that now with just any variable we want. Good so far?
Yep.
So now what's that equal to? That's going to be, we got to multiply this out. 6 times 6 is, so 16 times, 6 times 6 is, we'll just call it 6 squared. And then we have 6 times delta t, and delta t times 6 is going to be plus 2 times 6 times delta t.
Okay.
Right? And then delta t times delta t is delta t squared. And then we have minus 16 times 6 squared all over delta t. Anything weird?
I think we're good.
Okay. So now 16 times 6 squared is 16 6 squared. But we have a negative one of those right there.
Yeah.
So that one will cancel out.
Yep.
So we still have the 16 times 2 times 6 times delta t. Multiplying that to that.
Yeah.
Plus 16 times delta t squared. Multiplying that to that. All over
Delta t.
delta t. Now notice that has a delta t in it and that has a delta t in it, so I can cancel out the delta t's, top and bottom. Factor a delta t out of both these and then cancel it out.
Yeah.
Okay, so that is going to be equal to 16 times 2 times 6. 16 times 2 is just 32. Well, I'll rewrite that one out, but we want to leave the 6 isolated for now. So that's going to be 32 times 6
Plus 16.
plus 16 delta t. This still has one delta t. We can only cancel out one of its delta t's. All over delta t. Oh no, the delta t's gone. We canceled it out. And now we can take its limit. And what's the limit as delta t goes to 0?
0.
This goes to 0, so it's just 32
Times 6.
times 6.
Yep.
Now that's when we plug 6 into this function. So 32 times 6, whatever that is how fast it's falling after 6 seconds. But there's nothing special about that 6. We could have plugged in any time t naught that we wanted. And just replace all your 6's with t naughts, and it comes out t naught here.
Yep.
So, what is the speed at 0 seconds?
0.
0. The instant you drop that rock, it's not moving. After 1 second, how fast is the rock falling?
32.
32 feet per second. After 2 seconds, how fast is that rock falling?
64.
64 feet per second. Etc., right?
Yeah.
Okay. So that's finding the speed of the rock at any point. So if you graph the position of some object with respect to time, its derivative gives you the speed at any time. Or the velocity.
The velocity under it. Under the
Yeah.
line.
And notice that, since you're in physics, show you this, we could have just as easily written this as f of t is equal to some acceleration times t squared, right?
Yeah.
Then what is f prime of t? It's just equal to 2 times the acceleration times the time. That's all we did. We just took the 16, multiplied it by 2.
Oh yeah, okay.
And so whatever that 16 was, this is just double 16. So whatever your acceleration was, down here when you get into velocity, you just double it and multiply by the time.
So
In the case where we're talking about an object falling.
Yeah. So you find velocity, just the area underneath the line?
No, the velocity is the slope of the function.
Okay.
Think about if I was just walking at a normal speed.
Yeah.
So my velocity stays the same, my speed stays the same. What would, if this was graphing my position with respect to time, what does it look like? Just a line.
Just going up, yeah.
But it's going up like a line.
Yeah.
And so the slope of the line is my speed.
I'm pretty sure my textbook said that you can calculate the velocity of something is the area underneath it.
Now, if you graph the velocity, then your position is the area underneath your velocity curve.
Okay.
So you got it backwards.
Okay, I gotcha.
Graph position, the slope gives you your velocity. Graph velocity, the area under gives you your position.
Position. Okay.
Or displacement. Okay. So we did that, we did that. Good?
Yeah.
Move forward. I don't know, I'll need to make reference to them. So we'll just stay on the chalkboard just in case. Okay. So, now the actual definition that you'll see in your book for the definition of the derivative of a function. Here's the exact definition that I give you. F prime of x, your derivative of f with respect to x, is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Logically equivalent to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Which is the same thing as, here's the other way they like to write it. Notice that this is doing the exact same thing as this, except for swapping the z and the x.
Yep.
So, it's the same thing as the limit as z approaches x of f of x minus f of z over x minus z.
Okay.
That is a derivative of a function. It gives you this new function. You take that derivative, spits out a new function.
Yep.
Okay, notation. To talk about the derivative, we use the notation f prime of x. We also use y prime, because if you have y equals f of x, then y prime is equal to f prime of x. Same thing.
Oh.
That's where the y prime comes from.
Okay.
dy dx, where does this come from? Common substitution in mathematics. If I take the limit as delta x approaches 0 of delta y over delta x, then we usually replace that with a dy dx.
D meaning derivative. Done.
Yeah, this is all notation saying the same thing. This is saying the derivative of y with respect to x. I'm showing you where the notation comes from.
Okay.
Comes from replacing the delta y and the delta x. This is when you're doing it over some distance. These ones you can think about as being instantaneous, arbitrarily small.
Okay.
Make sense?
Yep.
And then you also have the derivative of f with respect to x. That's the same as this, just replacing the y with the f. We also sometimes think about the derivative as an operator. So this is saying the derivative with respect to x of f of x, or the derivative with respect to x of f of x. All notations saying the same thing.
Okay.
A little bit frustrating that we have so much notation to talk about it. You feel like you're drowning in notation. These three are the ones that are most frequently used. And I doubt you'll even see this again until Calc 3.
Okay.
All notation for the same thing. Good? All right, so let's go through the next section's examples, and then one little theorem, and then we're done. So the next thing the author wants us to do is they want us to differentiate. So it says differentiate f of x is equal to x over x minus 1. Now what does it mean when it says differentiate it? It means find the derivative. Same thing.
Okay.
So we're going to find the derivative of this. I'll just use the author's definition. So we are trying to find the limit as h approaches 0 of f of x plus h. I'm going to plug in x plus h here. So we're plugging in x plus h for this. So x plus h over x plus h minus 1 minus what you get when you plug in x minus f of x. So in that case, it's going to be minus x over x minus 1 all over h. With me? Okay, so we got to calculate this limit. What's that equal to? Let's work with the inside. I've got two different terms. I need to get a common denominator in the numerator. I need to multiply this one top and bottom by x minus 1, and multiply this one top and bottom by x plus h minus 1. Right?
Okay.
Okay, so over this one, I'm multiplying top and bottom by x minus 1. So that is going to be x plus h times x minus 1 all over x minus 1 times x plus h minus 1. So rewrote this term, multiplying it top and bottom by x minus 1. Minus this term. I need to multiply top and bottom by x plus h minus 1. So that's going to be x times x plus h minus 1 all over x minus 1 times x plus h minus 1, right?
Yep.
And we take that whole thing and multiply it by 1 over h, which is the same thing as dividing it by h, right?
Yeah.
Okay, so now what's that equal to? Come over here and keep on going.
Okay.
So notice that we're going to have a common denominator here, right?
Yeah.
So I'll write all over the same denominator and multiply these out as we go. X times x gives me x squared. X times negative 1 gives me minus x. H times x gives me plus hx. H times negative 1 gives me minus h. So I multiplied these two out, right?
Yeah.
And now I need to multiply x to each one of these things and then flip the sign on each of them because it's negative. So x times x is,
X squared.
make it negative, so minus x squared. X times h is,
Negative H.
okay, you're thinking ahead, yes. And then x times negative 1, make it negative, is plus x. You with me?
Yep.
All over, x minus 1 times x plus h minus 1. I'm not going to bother multiplying that out because it's something, I need something in the top to cancel out with that h. So I'm not going to mess with the bottom, and then all of this times 1 over h. Good? Okay, now lots of things better cancel or else we did something wrong. X squared, negative x squared. So that cancels with that. Negative hx, hx, x, negative x. What am I left with?
Negative h.
Negative h. All over x minus 1 times x plus h minus 1 all times 1 over h. Right? And now we can cancel out h top and bottom. And with that, we'll be ready to take our limit. So this is equal to negative 1 all over x minus 1 times x plus h minus 1. Now we're ready to take our limit. And our limit is just replacing h with 0, right?
Yep.
So this is just going to be all equal to negative 1 over x minus 1, so x minus 1 squared. And that's the answer he has.
Sweet.
Good? All right, let's do his next example. He wants us to find the derivative of f of x equal to the square root of x. So this time we've got f of x is equal to the square root of x, where x is greater than 0. Notice the square root function, if we scribble that to the side here really quick, what can't we plug into the square root function?
Negatives.
Negative numbers. And so our square root function, it starts at 0, and then it shoots off like this.
Yep. That makes sense.
Okay, so we're looking for the slope of this function at any point. We're looking for the derivative of this function, where x is greater than 0. What about at the point x equal to 0?
That's not true.
Can you find the slope of this thing at the point 0?
No, it will be undefined, won't it?
Why would it be undefined?
Yeah, you can.
So we have our slope right here is like that, right?
Yeah.
As our point gets closer and closer to 0, what is happening to our slope?
It's getting bigger.
It's getting bigger and bigger and approaching what?
Undefined.
Undefined. So it should be so when we get our derivative, we better see that this thing doesn't have a slope at 0
Oh.
because it's straight up.
Yeah.
And what's the slope of a vertical line?
Undefined.
Undefined. Okay, so that's why notice that the square root function, it's defined at 0. It's continuous at 0, but it's not going to have a slope at 0. So just because the function is continuous at a point doesn't mean it has a slope at that point. Make sense?
Yep.
Okay, so let's calculate the derivative of this thing. He says to do it at the point x equal to 4. We'll just do it in general, and then we can plug in 4.
Okay.
Make sense? All right, which definition should we use?
H.
The H one? We just did that one. Let's do this one.
Okay.
Okay? So, I'm looking for, I want to find the limit now. As z approaches x of our function, f of x minus f of z. So what's f of x?
Root of x.
Square root of x. Minus f of z,
Root Z.
which is just the square root of z, all over x minus z. Have I done anything weird so far? I've just plugged into this. You see how I'm just flat out, just blindly plugging into our definition.
Yeah, we're good.
Okay, so now we got to evaluate that thing. Oh, we've got radicals. What do we do when we've got radicals? So first off, notice the denominator is going to 0. That's always a problem.
Yeah.
We got to cancel that out. We've got radicals in the numerator. What should we always do when we have radicals in the numerator?
Multiply it by a weird form of 1.
Multiply it by a weird form of 1. What's the form of 1?
The opposite of the numerator.
The conjugate.
Conjugate.
Oh,
That's
Same thing, just flip the signs.
For everything this time.
So we're just going to multiply as top and bottom by the square root of x plus the square root of z over the square root of x plus the square root of z. Why are we multiplying by that special value? It's the one that's going to get rid of all our square roots. We don't want those square roots in the numerator.
Just removes them.
So it gets rid of our square roots. How does it get rid of our square roots? Let's multiply it out. What's the square root of x times the square root of x?
X.
X. What's the square root of x times the square root of z?
Square root of x, square root of z.
Yeah, it's the square root of x times z. Or you could have left it square root of x times square root of z. Both of those are fine. Okay. What's negative z times the square root of x?
negative
Negative z times x.
Negative square root of
x.
x times z. And then finally, what is negative square root of z times the square root of z?
Negative z.
Negative z. And notice these two terms
Cancel each other
Cancel.
out.
cancel out. That's the whole reason we choose this.
Yeah.
Gets rid of all your radicals. And so this is all over x minus z. With the bottom, we're never going to bother trying to distribute this out. All right, so far you're with me?
Yes.
This in parentheses. Okay, and that is all equal to, we'll just come right all the way over here. And that is all equal to, in our numerator now, we just have what?
X minus z.
X minus z. And in our denominator, we have x minus z times square root of x plus square root of,
Oh.
Z.
Okay. Yep. I see.
right?
So when you're multiplying by the conjugate, is it better to not multiply it out on the denominator?
I would never bother multiplying it out on the denominator because your whole goal is you're trying to get this term to cancel out. And so if you multiply it out, you're going to lose that term. And it's still going to go to 0. It's just going to be weird to you that it keeps going to 0. You can't figure out how. So you did that on your test. You tried multiplying by one thing, it was going to 0 over 0. Oh, well, there we go, 0 over 0. I guess that's the answer. Don't remember who wrote that. I wrote a big old no on your paper. Never divide by 0.
Not me.
Yeah, it's by Caleb.
Huh?
By Caleb.
Probably.
It's Caleb. He told me. He did.
Whatever it is, so leave that term alone because our whole goal was cancel that out. And now, notice, that's what we got to show up in the top.
Yep.
And so now, put parentheses around it. That helps you think x minus z, cross out with x minus z. And we're left with, in the numerator, just 0, right?
No.
No. What's in our numerator?
1.
1.
1. Okay, just making sure. All over the square root of x plus the square root of z. And now we got rid of the term that kept going to 0 in the denominator on us. And so now we can just take our limit. So now we're ready for our limit. What were we taking the limit of? The limit as z approaches x.
Oh.
So what does z approach?
X.
So what does the square root of z approach I mean?
X.
Square root of x, right? And so this is going to be the 1 over the square root of x plus the square root of x.
Which is X.
Okay. For all the marbles, what is the square root of x plus the square root of x?
2 times the square root of x.
It's 2 square roots of x,
Which is what that represents anyway.
which is 2 square roots of x. It is not equal to x. Not by a mile,
Yeah, that's right.
right? What's the square root of 9?
3,
So square root of 9 plus square root of 9 is
6.
not 9.
Yeah,
Yeah, okay. What's an apple plus an apple?
an orange.
2 apples. What's the square root of x plus the square root of x? 2 square roots of x. A thing plus a thing? 2 things. Whatever those things are. And so, the answer here is just 1 over 2 square roots of x. Okay, now he told us, or he asked us to, find the slope at the point 4. So over here at 4, what's the slope of this function?
1/4.
1/4. And our picture, can't trust it too much, but 1/4 sounds about right. It's increasing very shallowly. Shallow.
Shall.
It's not very steep. Right?
Yep.
So there we go. All right. Next example. Should say that the author inside the book, these first 2 chapters, he gets very precise pictures showing you the picture and then the picture of its derivative function to help you get intuition for how, I tried doing it with some simpler ones, how the derivative is graphing the slope. So he's got some nice pictures and some nice examples that I'm not going to write up here because I'm not going to draw out the pictures that he has. But it's worth a read so that you can see more precise stuff than what I can just draw
Yeah.
really quick. All right, so the next real one he does is the square, or not the square, the absolute value function. So now, this time, we have f of x is equal to the absolute value of x. And we're looking for the slope of that thing.
Okay.
Okay? Now, how do we work with something like that?
Plug it in.
Well, we can go ahead and plug it in. Okay, so which one do you want to plug it into?
Delta X.
You want to use the delta x one? So, we've got the limit as delta x approaches 0 of the absolute value of x plus delta x minus the absolute value of x all over delta x, right?
Yep.
Okay, now what? You notice that you're probably going to get a bit stuck here because we need to break this up into 2 cases. So think pictorially what our absolute value function looks like. What does the absolute value function look like?
V.
It looks like a V. Yeah. It comes down like this and then shoots up like this.
How do you ever get a negative number? It's an absolute value. It's just distance.
What is this saying? Plug in -4 and what do you get?
4.
4. Plug in 4 and what do you get?
Okay, I get you.
4. Alright, yep. Oh, I was going to take the time to mention, remember going back here, this was a slope to our square root function. Notice what happens when you plug in 0.
Undefined.
Undefined. So I forgot to make that special note, which is what we expected.
Okay.
Okay, so now jumping back to this function, notice, just by looking at the picture, what's the slope over here at -3?
3. Oh.
The slope. What's the slope?
Negative 1.
-1. The slope here, -1. The slope here, -1. The slope here, -1. -1, -1, -1. What's the slope here?
1.
Negative.
+1, +1, +1. No,
I just said that.
So is it
Negative.
piecewise
positive. So it has a piecewise definition, and we're going to have to do a piecewise derivative. We're going to need to do the derivative of the function for all the points that are less than 0, and then the derivative for the function for all the points that are greater than 0. And then what about at 0? What's the slope of the function going to be at 0?
0.
0? So the slope is intuitively, what is the slope of a function at a point? You draw the tangent line to that point, and whatever the slope of the tangent line is what the slope of the function is. Right? Intuitively, but that's what we're after. So when I say what is the slope of, if I give you some function, and I say what's the slope at this point, you have to find the one and only line that goes through just that point, and it doesn't intersect the function anywhere else. That's called its tangent line. And then the slope of that tangent line is the slope at that point.
Yep.
How many tangent lines does this point have?
1. Infinite.
Infinitely many. I can draw a line that goes like this, and it only intersects at that point. I can draw a line that goes like this, and only intersects at that point.
Well, it doesn't have infinite. There's holes.
No, there's an infinite number of lines I could draw that only go through that point.
Yeah.
So it has an infinite number of tangent lines. So which tangent line do we use to get its slope?
The flat one.
You just like that one the most because it's somehow the average, so it's appealing to you in some way? The point is there is no way to talk about the slope at a point.
So that's a bad question.
So we're going to see that it's not going to make sense to talk about the slope of this function at 0, and that's what we expect. So there's going to be a couple ways that we can't talk about your function having a slope. One of the ways is your function becomes vertical. So if we look at a cubic function, that's a good example. A cubic function, oh no, that's not a good example, because it's 0 there. But if we look at a function that goes something like, it goes up, and that has a period where it's straight up, and then continues on its way,
Yeah.
there, it shouldn't have a derivative. Shouldn't have a slope.
Well, because it's vertical.
Right. So that's one case where it doesn't have a slope. Obviously, it also doesn't have a slope if it's not defined there, right?
Which is every case, wouldn't it be?
If it's not defined there, then it can't have a slope there.
Yeah.
So going back to this function, what was its slope at 0?
Undefined.
Bad question, yeah, undefined. Because it's not even defined there.
Yeah.
So I'll talk about where we expect not to get slopes.
Wouldn't that only be when it's undefined?
So here's an example. No, corners, sharp edges. If I've got a function that goes like this, at any of these points, I don't expect it to have a slope.
Oh. Yeah.
You can't do the slope right at a sharp point, right at a corner.
Okay.
So those are going to be cases where it doesn't have a slope.
Why can't you?
Well, we'll see with the example here why the absolute value function doesn't have a slope.
Okay.
So yeah, we'll see very concretely why it doesn't have a slope. Because what is a derivative? It is the limit of this. If this thing doesn't have a limit at 0, then we can't talk about its slope at 0.
Yeah.
And we'll show that it doesn't have a limit at 0. So let's take the limit as delta x approaches 0, but let's handle the case where all of our x's are greater than 0. So in this case, all our x's are greater than 0. You with me? So if x is greater than 0, then it's going to be positive.
Yeah.
And so our absolute value of x is going to be
Positive.
just x. So the absolute value of this is just going to be x plus delta x minus the absolute value of x is going to be x when x is greater than 0.
Yes.
Maybe scribble our definition of absolute value up here really quick. What is the absolute value of x? It's equal to x if x is greater than 0. It's equal to 0 if x is equal to 0. And it's equal to negative x if x is less than 0. Right?
Yeah.
Okay, so in the case where x is greater than 0, so we're only taking the derivative for the right-hand side of our function, then the absolute value of x is just going to be x.
Yeah.
Okay, all over delta x. You with me?
Yep.
Now, x and negative x add up to
0.
0, so we get delta x over delta x. What's anything divided by itself?
1.
1. Now take our limit. What's our limit of 1 as delta x approaches 0?
1.
1.
So why is that?
Well, now let's do our limit as delta x approaches 0. But this time, we'll only look at x is less than 0 on the left-hand side.
Okay.
With me? Okay, so in this case, we get the absolute value of x plus delta x minus the absolute value of x all over delta x, right? And now when we take our absolute value, what is it? It's negative x. If x is less than 0, we spout negative x. So in this case, it's going to be negative x minus delta x, and then minus negative x is going to be plus x. You with me? All over delta x. Negative x and x cancel out, and so we're left with negative delta x over delta x. 1? Negative 1. Now take the limit, and what do we get?
1.
The limit of negative 1 is negative 1. Okay, so let's graph this thing's derivative function. What did we get? For all our values greater than 0, we got 1. So it looks like this. For all our values less than 0, we got negative 1. What is the limit of this function at the point 0? Undefined. How do you know? Because it has a different limit coming from the right than it has coming from the left. And so it's undefined. And so this quotient, the definition of a derivative, is actually undefined at 0. So pictorially, since our function was a v, our intuition was telling us it should be undefined. But actually, when we work through the math, we still get that it's undefined. Approaching 0 from the left, we get negative 1. Approaching 0 from the right, we get positive 1. So the limit doesn't exist at that point. Okay. We'll shove over to our whiteboard. And I've almost got the whole thing. Should we get up to here? Got some new markers. These were dying on me. Sorry, what?
So that was surprisingly accurate when you drew that line.
Okay. So we did that. We already did that. Okay. So yeah, last thing is just some definitions and then our theorem, and we're done. Okay. So definition. So what did it mean when we said that a function was continuous?
It means that for the limit of any point is equal to what you get for your output at that point.
Yeah, so the limit of a function at a point is equal to the value of the function at the point. But when I say a whole function is continuous, that's just shorthand for saying it's continuous at every single point in its domain. That's what it means. Similarly, when we talk about a function being differentiable, all that means is it has a derivative at every point in its domain. And if it doesn't have a derivative at every point in its domain, we say it's differentiable on this domain and this domain. So we would say that the absolute value of x is differentiable on negative infinity to 0, union together with 0 to infinity. It's differentiable on those open intervals because it's not differentiable at 0. Okay? So when we're saying it's differentiable on this domain, all we're saying is you can calculate derivative at all these points. That's all it means. And so when your book tells you differentiate the function, it means find the derivative. That's all it's saying to do. So precise definition. So definition, let y equal f of x, or the function y equal to f of x, is differentiable on some open interval a to b, if and only if it has a derivative at every point in the interval. Make sense? Now it's differentiable on some closed interval a to b, including the endpoints, if and only if it's differentiable on all the points a through b, not including a and b, and the limit as h approaches 0 from the right of taking the derivative of our function at the point a, at the left-hand point, spits out a number, and doing the same thing at the left-hand point spits out a number.
Yeah.
So here's some closed interval a to b. Here's an example of a function that is differentiable on this closed interval.
Yeah.
Why is it differentiable on this closed interval? Because you can calculate the slope on any of the points in between, and if we were to calculate the slope of this thing, as we approach A from the right, so our tangent line approaching it from the right, we're going to come up to a value. And similarly, approaching it from the left, we're going to come to a value. And so if we approach B from the left, taking its derivative, then we would get close to 0. Here we get close to, like, I don't know, 1.
Yeah.
Remind you of a function that wasn't differentiable this way. Going back to our square root function. Our square root function is not differentiable on the closed interval 0 to 2. We'll look at on the interval 0 to 2. What does it look like? It looks like this. The reason it's not is because as we take the limit approaching 0 from the right, we're going to get something vertical. It's going to be undefined.
I see.
Okay.
Just, I don't know, reminding you of it really quick. I'll write through it really fast this time. Let's take the limit as x approaches 0 from the right, so we're coming this way, of the square root function. So the square root of, which one should we use? Which definition do you want to use here?
Oh.
So we're doing it at a point. I'm just going to do this one. You okay with this?
Yeah.
So the f of x and the f of c. So we're having x is approaching 0. So 0 is going to be a stand-in for our c. Is equal to the square root of x minus the square root of 0 all over, right?
Yeah.
And so this is going to be equal to, we'll take the limit when we're done, it's just going to be the square root of x over x, which is going to be 1 over the square root of x. As that gets arbitrarily close to 0, your denominator is still blowing up going to 0.
Okay.
And so it's not defined. This limit doesn't exist for this one over here. If this would have come out to something, if I was using some other function, then we wouldn't have a problem and we would have gotten a number. And so it would have been a function more like this as we approach the point. So if it comes out to a number, it exists. If it's a limit you can't take, it doesn't exist. And in this case, it's shooting off to infinity. Right? We would have said this is equal to infinity, approaching from the right.
Yeah.
Meaning it has a horizontal asymptote there.
Yep.
Good? Okay, now our last thing to note. We talked about how a function can be continuous at a point and still not have a derivative at that point. That was our absolute value function. Notice our absolute value function is a continuous function. There's no holes in it. But it's not a differentiable function at that point. So just because it's continuous doesn't mean it's differentiable. What about the converse? Is it true that if it's differentiable, then it's continuous? Is it true that if you can find a slope at a point, it must be continuous at that point?
Yes.
Turns out, yes. And that's what this final thing is going to prove. So if f of x is differentiable at some point x equal to c, then f of x is continuous at the point f of x equal to c. And that's what we're going to prove.
Okay.
So what do we assume? Assume f of x
Number.
is differentiable at x equal to c. And I'm going to show that if that's true, then it must be continuous at x equal to c. Let's write some scratch work to the side. What does it mean for f of x to be differentiable at c? That means that we can calculate the derivative and get a number.
Yeah.
So that means then the limit as x approaches c of f of x minus f of c
Over.
all over x minus c has to equal something. It has to exist.
So epsilon.
Has to equal some, well, you're used to calling that L, the limit of the thing.
Oh.
Now I'm not going to call it L because this is a special limit that we already have special notation for. We call it f prime of c, the slope of the function at c, f prime of c. So this is functioning the same as your L. This is just a very special L. You with me?
Yep.
So I know that that's the case. What am I trying to prove? I'm trying to prove that the limit as x approaches c of f of x is equal to f of c. What does it mean for a function to be continuous at that point? It means the limit of the function at that point is equal to the value of the function at that point. So I'm trying to prove that this is the case.
Okay.
I know that this is the case. I'm trying to prove that this is the case. With me?
Yep.
Okay, 3. Then, so that's the limit we're trying to calculate. I need to calculate the limit as x approaches c of f of x. I need to prove that that's equal to f of c.
Yeah.
Okay, f of x is for sure equal to f of x minus f of c plus f of c. I haven't cheated, right?
You have not cheated.
Right? No cheat. I just subtracted f of c and added f of c.
Okay.
Okay. I'm going to multiply and divide these two, top and bottom. So I'm going to multiply these two together by 1. So think about these two being grouped together. And I'm going to multiply them by 1. A very special one. So this is equal to f of x minus f of c divided by x minus c times x minus c. So I took these terms, multiplied top and bottom by x minus c, and I still have this plus f of c. With me?
Oh, okay.
Now we know what this equals when we take its limit. Maybe we won't take the limit yet. Well, should we go ahead and take the limit now?
Sure.
Let's go ahead and take the limit now. So now this is equal to, what's the limit of this piece equal to?
Zero.
F prime of c. What is the limit as x approaches c of f of x minus f of c over x minus c? F prime of c. That's what we were assuming. So this is f prime of c, some number. We don't know what that number is. Could have called it big L too if you wanted.
Yeah.
Some limit times, as x approaches c, what does x minus c get closer and closer to?
0.
0. As x approaches c, we get c minus c, which is 0. So that's times 0 plus f of c. What's 0 times any number?
0.
Plus f of c,
F of C.
which is what we were after.
That's cheating.
We showed that the limit as x approaches c of f of x is equal to f of c. Good? Alright, that's it for those two sections. You can go ahead, go on break, and then you get the rest of the class to start on your homework.
Are you going to be here at 5:30?
Probably not.